I'm Ms. Vung. Let's have a look at absolute maximum and absolute minimums. So what is absolute maximum? So let's say we have this graph over here and we're looking between the interval A and B. So in this interval, we notice that there is a local maximum up here and the highest value between X and B. So the highest Y value is also this point here. We call the highest Y value absolute maximum. Now you can start to understand why the local maximum, the turning point, is called local, because in that small area, it's the highest point. But in the whole domain, the absolute value, the absolute maximum means the tallest in the whole domain. What about if we had the same graph, but we change our domain between A and B to be all the way over here and all the way over there? Now the local maximum will be the same. So an area where it's the highest point, local maximum is still there. But we can see that in this interval here between A and B, that the highest Y value is not that point, it's actually that point over there. So the absolute maximum is that end point. So we can see the absolute maximum can be a turning point or an end point. The absolute maximum or minimum may be the value of the function at one end of a specified interval or the local maximum or minimum. So let's try some examples. Here we have a graph and let's analyze and find the local maximum and minimums and the absolute maximum and minimums. Now the local maximum means an area where it's highest. We can see the two turning points are at 1, 3 and at 4, 7. Whereas the local minimums, we can see that there's one at -2, -1 and there's another one at 2, -2. Now the absolute maximum for this section of the graph here, we can see the tallest value is over there at 4, 7. And the absolute minimum is not one of the local minimum, it's at 6, -5. Example 2, let's go through a series of the same graph with different domains so that we can identify what the local maximum minimums are and what are the absolute maximum and minimums are. So for the first part, 2A, we're going to look at if the domain was R or all real values. So it's a graph that looks like that and it keeps going, okay? Make sure that you understand it keeps going because the domain is R. Now in this case, we obviously don't see a local maximum or a maximum turning point, but we do see a local minimum at 2, -4. And the absolute maximum doesn't exist because this graph keeps on going. But the absolute minimum does exist. The lowest point is at 2, -4. What if we did the same graph but we change the domain to 1, 3? Now the graph will look something like so. And we can see again, we don't have a local maximum and we do have a local minimum at 2, -4. But now we do have absolute maximum or the Y value over there. So the absolute highest Y value or the absolute maximum happens at 1, -3 and 3, -3. So absolute maximum, the highest Y values are those 2 points over there. The absolute minimum is the same as the previous question 2A, which is 2, -4. Let's try 2C, where it's the same question again, but the domain this time is 3, 5. Do we have a local maximum? No. Do we have a local minimum this time? No. Do we have an absolute maximum? Yes, that point over there at 5, 5. And do we have an absolute minimum? Yes, this bottom point here at 3, -3. What about if we had the same question again, but we change the domain to -1 to 5, where -1 is exclusive and 5 is inclusive? We can see that the local maximum doesn't exist still, and the local minimum is still the same at 2, -4. But the absolute maximum is now not two values, even though they look very similar, but it's only the value on the right because that's inclusive. So the 5, 5 is slightly higher than the -1, 5. So the absolute maximum would be 5, 5. And again, the absolute minimum will be the same, 2, -4. Here's a summary of the 4 different graphs, and you can see and compare what absolute maximum is by looking at different graphs and how it occurs and when it doesn't occur. We can see that for 2b and 2d, the absolute maximums occur twice here and occurred only once because of the domain was not inclusive for the left side. So be very careful when you read the domain. Example 3. An open box with height x centimeters is created from a square piece of cardboard of side length 30 centimeters. So we have a square that's 30 centimeters, and then we cut off x amount, so little squares of x. So this section here was 30 minus x from both sides. So this smaller section would be 30 minus the 2x. Now if I was to close the sides, I would get a box. Again, it's not proportional. And the bottom of the box would be that square with the dashed line. So the side would be 30 minus 2x, and the other side would also be 30 minus 2x, and the height of the box would be x. Now it says find the volume of the box, so it's that times that times that. So 30 minus 2x times itself, so squared, times x. Then when we expand it, we have 900 minus 2x times 30 is minus 60 times 2 is minus 120x. 2x squared is 4x squared. And then we have to multiply all that by x. So, and I'm going to rearrange it so the highest power is to the left. So 4x squared times x is 4x cubed, minus 120x times x is minus 120x squared, and 900 times x is 900x. So the volume of the box is that equation over there. Part B, find the value of x that gives the box its maximum volume and show that the volume is maximum for its value. So maximum means we're deriving it and letting it equal to 0, and show means we have to do that table. So dv dx would be 4 times 3 is 12x to the power of 3, take away 1 is 2. Then minus 120 times 2 is minus 240, x squared becomes just x, and 900x just becomes 900. Now letting all that equal to 0, we can use the CADs and solve, and we obtain 5, 15. If you've forgotten how to do it, we can quickly do it together. Okay, so what we did there was we differentiated the original equation and we obtained the derivative, and the next video I will show you how to do these on the calculator in detail. But what I want to show you is if I have an equation and I want to solve for 0, I would go action, advanced solve, I would let that equal to 0, so equal 0, hit enter, and we get x equals 5 and 15. So that's a quick way to do it using a calculator. So let's keep going. So we can have x equals 5. Sorry. Now when x equals 15, we notice that 30 minus the 2x would give me 0. So x cannot be 15, x has to be equal to 5 because the length cannot be 0. So you always have to do a test to make sure that you reject the one that doesn't work. So then we check the nature of the stationary point by putting it into the table. So when x is 5, we know that the gradient is 0. And we go to the left, which is x is 4. We go to the right, x is 6. We plug it into this equation here to find the gradient. And we notice that when x is 4, this equation is positive. And when x is 6, this equation gives me negative 108, which is negative, so going down. And so we have a local maximum. So when x is 5, the volume, which is the equation up there, is equal to 2000 centimeters cubed. So the maximum volume occurs at x equals 5, and it is 2000 centimeters cubed. Part C. If the height of the box must be at most 4, what will the maximum volume of the box be? Now this is similar to what we are talking about in this in the previous example, where we change the domain and now the maximum is different. It's probably the endpoint, but we'll check. So the graph looks something like this, and we can see that at 5 there's the turning point. But before 4 and up to 4, so at most 4, we can see that the graph is always positive. It has a gradient greater than 0. So because it's strictly increasing, we can see that the maximum value is at 4. What does that mean? If the graph was on the other side, we can see the maximum value would be to the left. But because it's strictly increasing, the maximum value would be to the right. So then we plug in x equals 4 into the original equation and we obtain that the volume would be 1,936 centimeters cubed. That's it from me today. You might want to have a go at this again and I'll see you next time. Bye!